Okay, set up but do not evaluate the integrals that give the volume of the solid formed by revolving the region about the x-axis using disk method. Okay, so there are equations. Here are our boundaries, and we're revolving it around the x-axis to get that paraboloid, it's called. Chopping it up into these little thin things, and then disk around the horizontal line. It has a radius of... Okay, he forgot to square this here. So this should be r of x squared. So then you get this. The radius is just equal to the square root of x as you go along there. So then you're squaring the square root. And especially when you're doing these volume things, it is a good idea to put what variable your boundaries are of. And that is it. And he doesn't care what that is. Now, what if you spin it around the y-axis using something we're going to call the shell method? Or sorry, this is the disk method. All right, the instructions say shell method, so that threw me off. This should be disk method. We're still using the disk method. So now, when we do this thing, we're taking this thing and spinning it around here, and our disks, our washers, really, you know, look like, so you got this inner radius here, and this like that, and this outer radius that remains constant. So what you're really doing is you're finding the volume of cylinder, this cylinder thing, minus the area of this vortexy thing, and that leaves you with what you want. Okay, so you're taking the cylinder and subtracting the vortexy thing. So again, this is the cylinder, and this is the other thing. And that other thing on this particular bit looks like that. It's, you know, you're shading in that portion, and that's what you're finding out, and you're just putting this into terms of y, so then you switch that around, x equals y squared, and that is your volume. But that is a pain, and so there is a better way. And these instructions, and I'm not, okay, so instead of cutting this thing up into disks that go, you know, along, and we're still rotating around the y-axis this time. So instead of cutting this thing up into these things that look like this, and then you're cutting out this, and then you're finding the difference, which gives you this, and adding those things up, instead of summing up those donut-y things, instead, we're going to sum up a bunch of toilet paper roll-y things that look like that. Okay, so this is what our solid looks like. And, whoops, that's overrolling. Okay, so we're cutting it into these toilet paper rolly things, and they have a width of dx. So you imagine, like, with respect to the picture of the graph here, this thing is going to look like, the toilet paper rolly thing is going to go around like that on the back and come around here, and it's got this width dx there, and then its height is equal to the height of the orange thing. And so it looks kind of like that, even though the drawing's awful. And so that's drawn amazingly right here. And you can see that, and this bit right here is the radius. Well, what's the volume of this thing? You know, before we chopped this figure up into a bunch of, you know, disks or washers and said, well, what's the volume of an infinitely thin washer? Well, now, what's the volume of an infinitely thin shell? We're going to call this, you know, these are shells. They look like shells. You're putting a bunch of shells inside each other. It's kind of like those Russian dolls. And so now, what's the volume of this shell? Well, if we unroll this thing, imagine, you know, unrolling like a piece of paper and then rolling it into a shell. Well, the height is however high the thing is. The length, this total distance around, is just the circumference of the circle, which is 2 pi r. And then its width is dx, which is a little tiny, tiny piece of infinitesimally small tiny xness. So this is tiny x. And this is your tiny x bit here, your dx. So the volume of that thing, you just multiply all those things together, since this is a rectangular prism now. So the volume around that, okay, so this is kind of a far jump right here, so I'll elaborate more. So now what you're doing, this is the volume of 1. So now you're going to take another one, and you're going to put it on the outside. And now you're going to put another one and put it on the inside. And you're going to keep doing that until you end up with something that looks like this, and there are a bunch of these. It's like you're looking at it from the top now, and there are a bunch of these little infinitely thin shells, and this is going from 0 to however far you want to integrate. So that's like your max. But in the meanwhile, when you're integrating, you're saying, well, what's the volume of an infinitely thin shell when I'm here? Now how about here? 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 And you do that infinitely many times with our wonderful, this idea of integration. And so you're adding these up. You're adding up all the 2 pi x times heights. This right here, 2 pi r times h times dx. Well, in this particular case, our radius is just x. So then we get 2 pi times h times the radius, which is just x, times dx. And that's just for one of them. So now if we plug in every single x that we possibly can within our limits, within our boundaries, then we're going to end up getting the total volume. And so then you just integrate all these things. And we're calling h of x. H of x is the height as a function of x. So how does the height of this shell, and graphically, the height is this length here of that orange little cross-sectional segment. That is h of x. And so h of x, in this particular case, is the square root of x, since that is our function. And so now we have a way to get the volume of this awkward thing without having to do any squaring and shifting things around like we did before. We're not taking differences anymore. We're just, finding out the volume in this way by imagining it as a bunch of little shells. So that's pretty useful. And I completely buried that integral. But it says the volume is equal to, I'll just write it out again. The volume is equal to 2 pi from this here, x equals 0 to x equals 4, since that is our rightmost boundary here. We stop adding up the shells after we get to 4 of x, since that's our radius factor. And think about it, these things get bigger and bigger as you go along, times the square root of x dx, and that is our volume. All right, so what about if you're going around the x-axis? Well, in this case, it's actually more difficult to use the shell method, and you'll see why, but we're going to do it anyways. So we have the same boundaries, the same bounding functions, but now we're spinning it around the x-axis to give us that paraboloid. But now if you can imagine the shells, it would look something like that, except they'd be perfect cylinders, but that gets the idea across. The circumference is 2 pi r. And again, now instead of a little change in x here, you have a little change in y there, but it's still the exact same idea. So now you have this change in y here as opposed to a change in x, but it's really the same idea. And again, this is in the y direction now, and so we're spinning the thing around this way, and it's going to reflect like that, and it's going to be this thing. Okay, so now, what is the length of this little orange thing? Or more so, what is the height at any given point? Well, the height in terms of y. See, when we're integrating it with respect to y, what we have to do is go along the y-axis and plug in all of these little infinitely many values on the way there. And so at each of those values, we need to associate it with some length here in some area of that rectangle in order to give us the volume of that shell. So what we do is, well, at any given point, at some point here, what's the height of that thing? Well, it's the difference between this thing right here and this thing right here at any given point. So like here, it's the difference between It is the difference between this bit and this bit. And in terms of y, this thing is 4, which gives you the outer boundary, and the minus y squared, you're subtracting y squared, because if you turn your head to the side, you can see that that is y squared. It's given as y equals x, but if you convert that, you can, pretty clearly see that x equals y squared, which I rewrote for no apparent reason. And so that is your height. That is your height as a function of y. So if you give me a y, I can tell you what the height is, and consequently, I can tell you what the volume is of this thing. And the volume of that cylinder is going to be 2 pi times y times h of y dy. So, going on here, shell around a horizontal line is just going to be given. So that's we're chopping it into shells, and it's saying volume, which is basically what I just wrote there, except you're integrating, and now you're integrating. I want to point something out. Your boundaries are from here to here, because you need to try every single y value from there to there, and that's going to give you, the end result that you want. You're going to cover the entire volume of the thing. And for this particular instance, we're just matching up y's and everything's in terms of y and setting up that integral, and that will give you the volume. But notice that in this case, you had to set up like the 4 minus y squared and get the difference of this thing, and it was a little harder than using the disk method originally, in which case you would have just had to integrate from 0 to 4, x equals 0 to 4 of pi times the square root of x squared, which was on the first one of the first slides. So this is easier in this case, but in that other case, if we back up here, in this particular case, the shell was actually easier, and the disk was a relative, well, I mean, it wasn't so much of a nightmare, but, it was a lot more of a nightmare than this was once you understand what's going on. All right, so this is just a summary of some stuff for a shell around the x-axis, which is a horizontal line. You have a little piece with width dy and length h, and it's h of y, since you need everything's in terms of y, and you always have that 2 pi on the outside to proportionify, to relate that to the circumference, which relates to the volume of each shell. Same thing with the volume here. And, this generalization, right minus left, that's just saying to, take the difference between, anything so you can get this length if it doesn't happen to be flush against an axis. And the exact same goes for the, if you're going around the y-axis, then you're going to be looking at things in terms of x. For the disks, it was the other way around. If you're, right. That's really it. And so now we're going to do another example. Perpendicular. And so if you're using the disk method, you're going to have a bunch of things that are perpendicular to your axis of rotation, and it's going to be in terms of y. It's going to be in terms of the same variable. We're rotating around y, and we put everything in terms of y. But now, so this is for disks, and look at that. That's a nightmare, right? Because you have to take this 1 minus 0, which gives you, which is giving you the volume of this outer cylinder, really. And then you're taking, you're adding this other portion, which gives you the volume of this parabola-ish thing in terms of the y minus 1 squared, which, lets you look at it if you turn your head sideways. And that's it, and it looks hideous. And it would be even more of a pain to evaluate. But now, if we look at it with the shell method, parashell, that's a parallel parashell. That's another way, it's kind of an acronym. It's not an acronym. It's a mnemonic device to remember parashell and perpendicular. Sounds like parallel and perpendicular. Now, all of our shells go this way, and you can imagine that the shells themselves would look like something like this. They would be bounded, and they'd look like this. That would be the tops of them, but the shells themselves would go down like this. And you have all these little cylinders, these happy shell cylinder things, and you know the volume of each one, and once you scroll through all of these x values, you can find out the total volume of the thing. And so to find the length of this one, well, it's just proportional to the graph, which is x squared minus 1. And so you have that x factor in there to take into account that the volume gets increasingly larger as you get farther away. And that 2 pi, that's your constant of proportionality. And that is it. So hopefully the shell method makes sense, and just think of it as stacking like toilet paper tubes or Russian dolls or something like that, or rolling sheets of paper, so that you're getting all of these different shells inside of each other. And it's just another way of looking at volume. And usually what you're going to see is for a given rotation around an axis, either the disk or shell method is going to be far easier. One of them is going to be pretty straightforward, and the other one will be a pain, and vice versa. If you rotate around the other axis, the other one will be easy, and the other one will be a pain. I don't want to make that generalization and say that that will always be the case, but pretty frequently you will see that one of them is far easier than the other around a given axis. So hopefully that was helpful, and I will see you when I start talking about arc length.